Hello, everyone, and welcome to another installment of Formal Methods for Philosophers of Science. This is the second lecture in which I'm going to talk about frequentist conceptions of scientific inference. And in this second lecture, I'm going to talk about confidence intervals and margins of error. The methodology of statistical testing that we've discussed last week, in particular in the form of null hypothesis statistical testing. It takes a certain statistical hypothesis as a starting point, and it models the research process as a confrontation of this particular statistical hypothesis with the empirical evidence, a confrontation of a pre-articulated probabilistic hypothesis with empirical data. But often we do not have particular statistical hypotheses to start from. Often in scientific research, the aim is to develop and extrapolate such hypotheses from data. So, in the form of confidence intervals, frequentist statisticians have developed a theoretical instrument for this purpose as well. To take again a very simple example, you may want to assess the probability of a certain feature within a certain population, or the frequency of this feature within the population. But you can only examine a small sample of this population and observe the relative frequency within that sample. And this is just a very simple and basic form of the problem of extrapolating statistical hypotheses from the data. Instead of just the frequency of a feature, you may want to find out the distribution of a larger range of properties or quantities. That would be a more complicated problem. Or you would be interested in correlation between different properties as they are expressed within a certain population, extrapolating that from a certain limited sample from of that population. So all these are slightly more complicated forms of the problem, but let's stick with the simple case. For example, social scientists might be interested in how large the proportion of German households is that do not have any savings. So they define a suitable selection procedure by which they can survey 1,000 randomly selected households and ask them about their savings. Of all 1,000 respondents, 350 say that their households do not have any savings. So, what now? What do we do? It's tempting to say, well, about 35% of German households do not have any savings. But from our discussions last week, you may remember that even if that's the case, if 35% of households in Germany do not have any savings, it is the case that getting exactly 350 such households when you examine a sample of 1,000 is the single most likely outcome, but nonetheless, it itself has a low probability. And at the same time, if the real frequency of such households within the German population is more or less different from 35%, there will always also be a more or less great probability that the number within your sample of 1,000 will be 350. So it's not a precise thing. So now again, you may be tempted to say, well, okay, but 35% is the most probable population frequency, given that in our sample we found 350. But note that this does not work within the frequentist framework, in the framework of frequentist statistics. For a frequentist, any proportion, the proportion of 35% or any other number of German households that in 2020 have no savings, that's not something that can even has a probability. Either the number is 35% or it is not. It's not a recurring event type. It's not something that is attributed a probability. It is either 35% or some other number. So because of this, frequentist statisticians take a slightly different approach. A thing that can be modeled as a recurring event, an event type, is the sampling of 1,000 German households in a given unchanging reality where there is a fixed proportion of households that don't have any savings. And now the basic idea is, if we were to repeatedly examine random samples of size n for a particular property, and the frequency of the property within the population is p, then we can expect that 95% of the time, the number of cases exhibiting the property within each sample will lie within 2 standard deviations of Pn. Pn is the mean, the mean number in the sample. In our case, 350 if P is 35%. And the sample size is always 1,000. So that's because of the features of the Gaussian distribution that we discussed, that 90%, 95% of the probabilities sit within that middle section between within 2 standard deviations from the mean. And of course, the same could be said about that 99% of the time, the number of cases exhibiting the property within each sample will lie within 3 standard deviations from Pn. So this is, here you have the basic idea behind the methodology of confidence intervals. The idea is now that with the aid of this logic, you can provide a sense of what the observed sample frequency says about the range of possible values for the real population frequency. Not that the real population frequency has a probability, but of course it is unknown, and so as far as we know, it could be a number of different frequencies within a range. And we don't know what the real proportion among German households is. We don't know that it is 35%, but we know that 95% of the time, using the techniques that we used, we should get a value that's no more than 2 standard deviations from the real value. Now, well, great, you say. So what's 2 standard deviations? And this is where your troubles begin, because it's actually not that simple. The short answer is we don't know what the relevant standard deviation is, because it depends, among other things, on the population frequency, the very thing that we are trying to estimate, that we're trying to find out. So repeatedly and randomly sampling 1,000 households is, from a statistical point of view, no different from running repeated series of 1,000 random experiments with a fixed probability. So the expected distribution is approximated by a Gaussian distribution where the standard deviation is calculated like this. I've put it a little bit differently. We usually put the n in the same term here under the square root sign, but you can also put it like this, and there you can easily see that the standard deviation, it varies with sample size. More precisely, it varies with the square root of the sample size. And it also varies with this interesting function of p. P is the probability of the event, of a certain outcome of the experiment, or in our example, the probability, the frequency of the feature within the sample, the real value, what in reality the proportion of households without any savings is, for example. So the standard deviation varies according to the square root of 1 minus p times p. So if you plot this function, this is just in the between 0 and 1, it's a function that describes a perfect circle. So you see that it has a maximum in the middle, that is around p equals 0.5. And in this mid-range, it doesn't change very much, but it goes to 1 towards this end and to 0 towards this end. And so another more hands-on feeling of the dependence of the standard deviation on the probability p can be gained by looking at distributions for a constant number of trials, in this case 50 trials, where we vary the probability of the outcomes. We can see that the normally distributed results are crowded together in a more narrow bell curve when the probability lies at either end of the sample spectrum. And then again around here at the end and around the middle range of probability, there is not so much change in the breadth of distributions when we change. So to the margins of the probability spectrum, close to 0, close to 1, less breadth in the distribution, smaller standard deviation, and in the middle, the breadth has the greatest variance. It's clear that the distribution has the greatest variance when p equals 1/2, corresponding to the maximum that we plotted in this function here. So hacking makes use of this fact to construct a very rough and ready kind of confidence interval. And the idea behind this is this: for p, if the probability is 1/2 exactly, then the standard deviation takes the value, this value, square root of n, half of the square root of n. Yeah? Just plug in 0.5 for p and you get this. And so standard deviations for smaller values of p, for all other values of p, will be smaller than that. I should have said all other values of p. Yeah. So 95% of the time, the number of cases in a sample of n will be within square root of n, so two of these, two standard deviations of Pn. For example, if in our example the sample size is 1000 and the real probability is 35%, they will be in within square root of n of 350, where p is the population frequency. Or put differently, not talking about the numbers of cases that we find, but the relative frequencies that we find in the sample, so not 350, but 0.035, 95% of the time, the sample frequency S will be within this divided by N of P, of the real frequency of the feature in the population. And square root of N divided by N is the same as 1 divided by square root of N. Therefore, Hacking's recipe for constructing a very simple kind of confidence interval is set the margin of error at this value, 1 divided by square root of N, and claim that within confidence level 95%, P lies in the confidence interval that ranges from S minus 1 divided by square root of N to S plus 1 divided by square root of N. So this is the typical way of constructing, this is the only way of constructing confidence intervals that we're going to look at. Namely, we take a mean, in this case, we just take as a mean, we take the frequency that we found in our sample, S, and then we take a margin of error, that's a number that we subtract from and add to the mean to get the limits of our confidence interval. You can also, for special applications, you can also construct asymmetric confidence intervals so that the margin is not the same on both sides of the mean, but we're not going to consider this as a possibility. We're just going to look at the most simple idea of using symmetric confidence intervals. Although you should keep in mind that if you consider this a possibility that you could use different margins on either side of the value that you're looking for, you realize that that's a degree of freedom. Yeah, you may construct different intervals, and the different intervals all have the feature that 95% of the cases you will be right, even though they are substantially different in giving different priorities to not underestimating or not overestimating the value that you're looking at. So, but this is the kind of result you get. You get a result that says with confidence level 95%, or you could also use a different confidence level, but this simple recipe assumes that you're looking for a 95% confidence level. With this confidence level, P lies in this and that confidence interval. So the first question, and in a way the most important question that I want to raise, is what does this mean? Let's first see what we get for our example. We get, for our example, with confidence level 95%, the proportion among German households that do not have any savings lies between 31.8% and 38.1%. So this is actually what you get when you apply Hacking's recipe to our example. You just take the sample frequency, which is 35%, and you construct the margin of error by means of this number, and then you plug the numbers in and you get this interval. Okay? But what does it mean? It has a certain appeal, intuitive appeal. You seem to understand what it means, but what exactly does it mean? So I'm going to quote Hacking on, because he put it very, very nicely. A confidence statement has the form: on the basis of our data, we estimate that an unknown quantity lies in an interval. The estimate is made according to a method that is right with probability at least 0.95. So that's what a confidence level statement of this form here, with confidence level 95%, P lies in the confidence interval I, what this means. It does not mean that the probability that P lies within I is now 95%. And that's a very important insight. This may not be obvious, and it's also sort of, well, it's often interpreted this way, and you can even find you can find sites on the internet that give a simple explanation of what a confidence interval is and that say exactly this, but that's not true. It is something that is unfortunately a little bit suggested by the term confidence and by also the terms confidence level and confidence interval. But note that, of course, a statement like that, the probability that P lies within a certain interval is 95%, does not make any sense within the framework of frequentist statistics, as I've noted before. P is a certain value that is realized in a real world example, and it is not something that occurs, it's not a frequency of anything. It's not a frequency of recurring events. I mean, I've perhaps called it a frequency, but it's in the sense of a distribution, of a fixed value within a population, a fixed value, fixed proportion with which certain feature is realized within a population. And there's no such thing as, I don't know, the number of histories of the universe in which the Germans in the year 2020 end up without savings with such and such in such a proportion. But you might say, like last week with a significant stuff, you might say, okay, yeah, I get it. The frequentists cannot say that, but as I am not a frequentist dogmatist, couldn't I still interpret the result like this and, like, in the back of my mind think, okay, officially you're not allowed to say that it's a probability, but really it's a probability? No. You will see that you're really making a mistake when you think about it like this. If you wanted to do it like that, if you want to think of probabilities, what's the probability now that the real value is in this interval, then you would have to make the switch to the Bayesian framework and think of it in Bayesian ways where you are allowed to do this. And if you do that and switch to the Bayesian framework, then you have to account for prior probability distributions. And this is something you need not do and you cannot do in the frequentist framework. So there are Bayesian techniques of constructing intervals for estimates, and they are called credence intervals. But the results can differ quite significantly from frequentist confidence intervals. And this can easily be illustrated. So suppose you get a random sample of 25 sets of personal data from the population of Iceland. It's a random, yeah. For example, you get random files from, I don't know, the central medical file registry from the Republic of Iceland. Suppose they have such a thing. And you examine it, and you find that there are only 5 men among these 25 randomly selected people from Iceland whose data you got. Now, simply following Hacking's instructions, we would have to conclude that with confidence level 95%, the proportion of men among the Icelandic population is between 0 and 40%. Now, as I said, Hacking's is a very rough and ready way of constructing confidence interval. And if you switch to a less rough and ready frequentist confidence interval construction than Hacking's, which we're going to briefly look at in a few minutes, then the results become even more bizarre, because if you get more precise and more narrow confidence interval, and you will get a result like the following: with 95% confidence level, the proportion of men in Iceland is between 4% and 36%. Now, if I say that the result is bizarre, the result is not bizarre as a result of confidence interval construction within the frequentist methodology, because it just says, well, this is an estimate that has been constructed according to a method that is right with probability at least 95. So at least 95% of the time. It only gets bizarre when you interpret it as saying that it is now 95% probable that the Icelandic population has only between 4 and 36% men. In Bayesian statistics, when you go and really want to find out, okay, how probable is it now that, how probable are different distributions of men and women in Iceland now in light of this little sample that we got, there you would start from a prior probability distribution that already reflects the expectation that the proportion of different sexes in any human population is most likely somewhere more or less close to 1/2. Not any population, of course. I mean, the Russian army is also a population in a statistical sense, but any population of any country, we have the prior expectation that its ceteris paribus, unless something really special has occurred, it is somewhere close to 1/2, and we would have a prior probability distribution that reflects this expectation, and then we would update it a little bit in the light of the sample. But in the end, of course, in the Bayesian view, you can reflect by estimating how probable you now think that different proportions are. You can, in that estimation, you can reflect the fact that you think it's much more likely that you just got a very, very rare case of a biased sample, which can happen just by chance with few men in it, then that the sample actually, that the proportion of men in Iceland is actually very low. So, and there's no way of accounting for this possibility within the frequentist framework. Frequentist conceptions have no way of incorporating that kind of information, that kind of prior distribution, the kind of prior expectation of different probability distributions. This is both the strength and the weakness of frequentist approaches. The strength is that we don't need this kind of information, which is sort of, as we've seen, hard to make precise, hard to make objective, hard to give an objective justification of. But the downside is that you have no way of providing this input, and that therefore also you will never be allowed to interpret a result like this constructed from a frequentist framework as saying something about how likely it now is, how probable it is now that the German population has a certain kind of proportion of households with no savings. So note that in cases where the prior probability distribution is less informative, so you have less informative prior ideas about where the probability might be, or we can make less instructive, reasonable assumptions about this at the outset. And you start the Bayesian analysis starts from a more equal distribution that reflecting indifference, then the interval estimates for unknown population frequencies will actually be quite similar to the respective confidence intervals in the frequentist framework. So it's good for philosophers of science to have some understanding, at least some basic understanding of the methodology and meaning of confidence intervals, because confidence intervals are quite often used to characterize the results in research publications in various fields. And it's even useful to get a bit of a feel for the numbers. So to do so, I'll start with Hacking's simple construction of a confidence interval. And I've calculated approximate confidence intervals calculated by Hacking's method for this is 95% confidence intervals for samples of various sizes and for an observed sample frequency of 0.5. So I've just quickly added the 95% here. So the idea is that you sample something and you get a sample frequency of 0.5. So, example, you have a sample of 10, and you get 5 out of 10. You find your property that you're looking for. So, what is the confidence interval? The confidence interval with a small sample like 10, calculated from Hacking, is somewhere between 18 and 81%. So that's actually, you see that a sample of 10 is basically no use to estimate anything. Yeah? And it's interesting that you can say this without knowing much more about the special case or so. That's just a fact of statistical error that is the same. It doesn't matter what it is that you're examining or you're sampling. If you have a small sample like this and you get a sample frequency somewhere in the middle, then the confidence interval will have a large margin of error, about more than 30%, a 95% confidence interval. And so actually for sample frequencies of 0.5, Hacking's method, so though it is a very rough and ready method, it is perfect or very good for these kinds of sample frequencies. Yeah? It gets more conservative, more generous for smaller or larger sample frequencies. If you look at the margin of error, if you look at that at 50, sample size 50, the margin of error is still 0.14. So you would getting half of your sample of 50 having a certain property, the confidence level still goes from 35% to 64%. Still a very, very rough estimate. And you need I mean, depending on what your expectations of this are, but you need samples of about like several hundreds to even get into ballpark um, precision. Yeah, if you have a sample of 500, then you can say, okay, this is somewhere between. And so you have a sample size of 500, you get 250 results of a certain kind, and you say, okay, the frequency of this result is somewhere between 45% and 55%. And then it gets more precise if you get larger numbers. So with 2000, you still have a margin of error of more than 2%. So Hacking's rough and ready method of constructing confidence intervals gives us conservative estimates because he takes the worst case. And the estimates are the more conservative, the further away from 0.5 the real population frequency is. Remember that he works from the fact that the standard deviation is largest for frequencies around 50%, and he uses the standard deviation for the case where the probability is 0.5 as a fit for all margin of error. That's just, well, margin of errors will at most be this, and then use that to estimate. Now, statisticians have developed more sophisticated techniques for constructing confidence intervals, reflecting the fact that when you move away from probability 0.5 in either direction, the breadth of the normal distribution gets narrower and standard deviations smaller. Remember that when I wiggled the value for the probability for the binomial distribution, that where the distribution got narrower towards the edge of the probability range and the most breadth in the middle. So you can therefore give smaller intervals in these cases where you have probabilities or sample frequencies closer to 0 or 1 than the middle. And you can give smaller confidence intervals and it will still be right 95% of the time. So I have calculated some numbers again from one such way of constructing a confidence interval. It's still a very rough and ready kind of confidence interval, and it doesn't live up to the standards of really sophisticated statistics, but it gives you a more realistic feel of what confidence interval will look like for different kinds of numbers. The table now starts from a smaller sample size, from a bigger sample size, from sample size 100, because this method here doesn't yield very good results for small samples. And note that, so these are lots of numbers, but of course, we're not going to look at all of them. I just want to give you a bit of an impression. Note, for example, the following thing. Confidence, so this is the sample frequency. This is for sample frequency 0.1, so 10%. You do have a smaller margin of error. Even like look at the small sample size, 100, the margin of error is now 5.9%, whereas in the middle of the probability distribution, if you have a sample frequency of 50%, then the margin of error is almost 10%. Yeah? So smaller margin of error towards the ends of the probability. But at the same time, it's still in the same order of magnitude, and it's still quite big for small samples. Yeah, still, for example, for a sample of 1,000, you still have a margin of error for 1.9%. So you estimate a certain thing, for example, how many people will uh, vote for the Liberal Party in the next election, and you ask 1,000 people, and you get like 100 who say they will vote for the Liberal Party, and your estimation at 95% confidence level is that the Liberal Party actually get between 8 and 12% of the vote. So you can see how difficult it is to predict, for example, things in the framework of the German 5% rule for elections, where you need to get at least 5% of the vote to get into parliament. Um, it really, these small differences count, and you read really, really large numbers for samples. So if you sample 50,000 people, you then have or also at 20,000, you already have a margin of error under 1%, so about 0.5%, which can still be quite large. Yeah? 0.5%, well, that can make the difference. It can easily make the difference. Another thing that you may note, if you compare these 5 different results, of course, by the way, I mean, the margin of error will be exactly the same on the other side of the of of 1/2. Yeah, this is symmetrical. So for a sample frequency of 60%, 0.6, you get exactly these margins of error, and for 70%, you get exactly these margins of error. So if you look at this range between 0.3 and 0.4, and you concentrate on the margins of error, not on the confidence intervals, which are, of course, different because they are around different values. This is, of course, then a confidence interval around 0.3. But if you concentrate on the margin of error, you can see that in this range, in the mid-range, in a generous sort of sense of mid-range, these are actually quite similar. The dependence on the sample frequency is actually not so strong. Yeah. For example, for 1,000, you get margin of error about 3%. And for 10,000, you get a margin of error of about 1%. These are fixed values. You can this is something that you can keep in mind, that for a sample of 10,000, if you look at something, find some feature in a sample of 10,000, and you have a sort of a mid-range sample frequency, then your margin of error will be about 1%. If you have 1,000, your margin of error will be about around 3%. Yeah. And if you have 100, then your margin of error will be about 10%. Yeah, and of course this here is very close to Hacking's construction. So you can see that Hacking's construction is really not that bad for it's very simplifying, but it's really not that bad for getting a grip, getting a feel for confidence intervals. So, and that's all I want you to get from this. I want you to get a feel for confidence intervals. I want you to understand a little bit of what they mean, because they occur so frequently in the research literature. And so I want to close today by noting just 2 things to conclude. One is that confidence intervals only account for statistical error. So they account for the kind of error that comes in because of the fact that there's chance involved in the in how your feature might actually be distributed in the random sample that you draw. Um, it only accounts for this kind of error. So if you draw different samples, then the feature will, even if it's perfect random procedure, the feature will always be slightly differently distributed within that sample, and that's the kind of error that the confidence intervals account for. It does not, for example, account for all sorts of bias that may happen within your um, research methodology, within your study design. In particular, it doesn't account for the effects of selection bias, which is the most pernicious and frequently observed kind of bias. So we've indulged in the fiction that we can somehow do real random sampling. Yeah, you can somehow, I don't know, make a lottery and sample households, German households. But that's of course not how it works. You call people on the phone, but that introduces a selection bias because not every family has a phone, perhaps. You do a survey by internet, but not everyone has internet, or they don't use it with the same frequency, and that means that your sample is not never in real life, never really a random sample of the population, and that's very, as every social scientist knows, that's very hard work to somehow approximate random sampling um, in real world research design. And this, you may be wrong there. You may not, that your model of your research methodology may be a better or worse approximation of random sampling. And this introduces additional error that's not covered by this idea of confidence intervals. So confidence intervals calculated like in the way that we've discussed so far say nothing about all these additional sources of error. I mean, if you think about experimental sciences, where you may also want to do statistical analysis of the data you get, there are error that may be introduced by imprecision of measurement. Imprecision of measurement can have a statistical element to it. It can be random, and that random effect can be estimated by means of confidence intervals, but it can also have more systematic sources of error, which are then not covered by the techniques that um, I've discussed today. So it's important to understand that confidence intervals constructed on the data with these simple statistical means do not yet account for all kinds of possibilities of error. Now, the second thing is just a reminder, I repeat that a confidence level of X%, that does not mean that it is now X% probable that the true value lies within the interval. What it means is that the estimate has been made according to a method that is right 90%, 95% of the time. And if you remember the example of Icelandic men, I hope that this is made clear that these two things are not the same. There's a difference between saying it's now X% probably is now 95% probable that the value is in the interval, or saying that it has been estimated with a method that is right 95% of the time, because your degree of belief, your overall estimation of the relevant probabilities may in the end say, well, okay, that's what I have now as the information, um, and in light of everything, taking everything into account, I think that this is probably a case where it's one of those 5% of the times where the method is not right. and that's what gets you in a direction of thinking about how probable it now is that the real value is such and such. But that's thinking beyond the methodology of um, confidence intervals. The confidence intervals say nothing about this. They just say this is an estimate that has been made with a methodology that is right 95% of the time. So, all right, that's all I wanted to say about confidence intervals, and that concludes my very, very brief and very, very superficial um, um, look at frequentist practices in um, for scientific inference. And yeah, I'm looking forward to discussing this with you at our online meeting.